Hello. Today we'll be talking about proofs and logic in a way that you'd understand. Let's get started. By the end of these lessons, you should have a firm understanding of the following vocabulary words: two-column proof, congruence, inductive reasoning, deductive reasoning, counterexample, conditional statement, converse, inverse, contrapositive, and biconditional statements. So let's get started by developing our understanding of the two-column proof. Now, in general, a proof is just a logical argument that is presented in an organized manner. We can do this in a number of ways. We can use a flow proof, a two-column proof, a paragraph proof, you name it. However, the most common form that we use in geometry is called the two-column proof. So let's consider the game of Uno when we're talking about two-column proofs. Now, in the game of Uno, you have 112 cards, and there are 4 sets of colored cards. We have blue cards, green cards, red cards, and yellow cards, all containing digits 0 to 9. Each of these cards has 3 types of specialty cards. We have skip cards, reverse cards, and the dreaded draw 2. In addition to this, there are also 2 types of wild cards. We have a regular wild card that changes the color, and we have a wild card that also makes you draw 4. So using the traditional rules, for each player's turn, the player matches the top card on the discard pile either by the number, the color, or the word, if it's a specialty card. If the player doesn't have anything that matches, then they must pick a card from the draw pile. But if the player draws a card that can be played, then the player must play that card. So what I've done is I've taken that game of Uno and I've turned it into a two-column proof. Remember, as we learned in the last unit, a two-column proof contains 2 columns. The left column, which contains statements, and the right column, which contains reasons that explain why that statement is true. So let's say that we start off with a green 8 in the discard pile. We want to figure out how we can end up with a yellow skip card at the very end. So if I start off with a green 8 card, that means that the next player can either play a green card or they can play any colored card with the number 8. And you'll notice that in statement number 2, the next player decided to play a blue card with the number 8. If we compare statement 1 to statement 2, you'll notice that for statement 2, the blue 8 matches the number of the previous card that was played. So now that we have a blue 8 on top of the discard pile, the next player must either play another blue card or they must play another card that contains the number 8. In our case, the next player didn't have a number 8, but they did have a blue 3. So that is the card that they played. And the reason why we can do that is because the blue 3 matches the color of the card on the discard pile. After that, for statement number 4, you'll notice the next player played a wild card. Remember, a wild card can be played at any time to change the color of the next card that's played. In our case, the person with the wild card decided that they wanted to change the color to yellow. This means that the next person must play a yellow card in order for the game to continue. And you'll see in statement number 5 that the next person played a yellow skip card. And this is perfectly reasonable because a yellow skip card matches the color of the wild card that we chose. And that is how we logically are given a green 8 card, and we have proved that we can end up with a yellow skip card. This is in general how all 2-column proofs work. We're given a statement to start with, and we have to end with a specific statement in order to prove that something is true logically. So let's try this together with the proof at the bottom here. If we start with a blue 5 card, how can we end up with a red 8? Well, if we look here, we can only make one move in order to get from blue to red. This means that we have to either match the color, match the number, or change the color entirely. We have a multitude of options that we can choose that would make this proof true. One of those options is to play a red 5 card. You'll notice that this matches the number of the previous card. So we can basically change the color of this card without having to do a wild card. However, a wild card would have also worked in this scenario if we used the wild card to change the color to red. But for now, we're using the red 5. After we play the red 5, the next person would play the red 8 because it matches the color of the red 5. And this is more or less how we complete a 2-column proof. Now that we know this information, let's try this with a geometric 2-column proof. Now, in Unit 1.3 about lines and angles, we also did a deep dive into the anatomy of a 2-column proof. Remember, we learned that in a 2-column proof, the given always goes first. And what you're trying to prove always goes last. There is no correct way or formula or method in order to complete a 2-column proof. You just have to make sure that each statement and reason follows a logical order and that it makes sense. Please also recall that we can use anything that we've learned in geometry as a reason. Most commonly, we use definitions and properties to explain our statements. Today, we're going to learn about one new thing that we can use as a reason. And that reason is called the definition of congruence. So if two figures have equal measures, then we can use the definition of congruence to prove that the figures are congruent. And we should know by now that the word congruent is represented by this symbol, the equal sign with the little squiggly on the top. Typically, we use the definition of congruence when we're either going from equal to congruent or from congruent to equal. For example, if we look at the proof in question number 1, you'll notice that statement 1 and 2 are pretty much identical. The only difference is that statement 1 goes from equal to congruent. Because of this, we can use the definition of congruence as our reason. And that completes the proof for question number 1. For proof number 2, we're filling in the 2 reasons that we see. As per usual, given always goes first. So reason number 1 should say given. Now, if we look at statement number 2, this says that angle 1 is congruent to angle 4. In order to figure out what our reason is, we should look at the diagram that's been provided to us. You'll notice on the right-hand side, we have 2 parallel lines, M and N, cut by a transversal T. What we want to do is look at the position of angle 1 and angle 4. Since these 2 angles are directly across from each other, that means that they are vertical angles. And we know from what we learned in Unit 1.3 that vertical angles are congruent. So our reason here is that vertical angles are congruent. And that completes proof number 2. Let's move on to number 3. For this third proof, we're given the fact that angle EFD plus angle BFD is equal to 90 degrees. What we're trying to do here is prove that angle CFA is equal to angle BFD. So as per usual, we're going to start with the given. Given always goes first. That's a no-brainer. However, for statement number 2, we're also going to have to figure out why angle CFA is congruent to angle BFD. To do that, we're going to use the same method that we just used in the previous problem. We're going to identify angle CFA, this angle, and we're going to identify angle BFD, this angle, on our diagram. Notice how, once again, these are 2 vertical angles. So our reason for statement number 2 is that vertical angles are congruent. Now we're going to determine our reason for statement number 3. If you look carefully, statement 2 and 3 are almost identical. The only difference is that we start out with congruent angles and end up with equal angles. If you think back to what we said a few minutes ago, when we go from congruent to equal or from equal to congruent, we would use the definition of congruence as our reason. So once again, the reason for statement 3 is the definition of congruence. And that is it for our 3 examples of 2-column proofs. If you would like, you can pause the video at this point and try out this proof with question number 4. You can also try out another proof with question number 5. Now we're going to move on to talk about logical statements. Now, a logical statement is just a sentence. And that sentence is meaningful in some way, shape, or form because any logical statement can be used to prove that something is true. So once again, logical statements are statements that allow us to draw a conclusion or a result based on some sort of hypothesis or premise. In layman's terms, they're just meaningful, declarative sentences that are either true or false. And in geometry, we have 5 main types of logical statements. That is the conditional statement, the converse, inverse, contrapositive, and the biconditional statement. Each of these would take a statement and either add a few words, negate it, or something of that nature. So let's talk about each different type. A conditional statement would take a sentence and add the words if and then. So we're going to highlight those keywords, if, then. The converse takes a statement and basically flips it around. In other words, the converse switches the order of the original statement. The inverse would keep the same order as the original statement. However, we would basically negate the entire statement. That means we would end up adding the word not to our statement, making the whole thing negative. Now, the contrapositive would take a statement and switch the order as well as making that statement negative. Finally, the biconditional is a special type of statement that contains the words if and only if. If we look at the upper right-hand corner of this page, we have a general summary of each type of statement and how it should be written. The conditional statement should say, if P, then Q. The converse should say, if Q, then P, because our statement is flipped. The inverse should say, if not P, then not Q, because we are negating the entire statement. The contrapositive should say, if not Q, then not P. And finally, the biconditional is a statement that says P if and only if Q. So now that we have an understanding of what a conditional, converse, inverse, contrapositive, and biconditional statement is, let's do an example where we write our own. For each sentence that we're given, we're going to rewrite it as the conditional, the converse, the inverse, the contrapositive, and the biconditional. But before we do that, we have to understand which part of our sentence represents P and which part of our sentence represents Q. So P always represents the first part or the first premise of our sentence. So in this case, the words students with an A represents P. The second half of our sentence that says do their work represents Q. So once again, we're going to take this statement and we're going to rewrite it 5 different ways using the conditional, the converse, the inverse, the contrapositive, and the biconditional. So let's get right into it. The conditional statement would say, if students have an A, then they do their work. If we compare it to the original, this is basically the same exact sentence. The only difference is that we've added if and then to the sentence. Now let's move on to the converse. The converse basically takes our statement and it flips it around. So our statement should say, if students do their work, then they have an A. Now let's move on to the inverse. The inverse is going to take our original statement and it is going to negate it. So we would say, if students do not have an A, then they do not do their work. Let's move on to the contrapositive. The contrapositive, again, is kind of like the inverse. What we're doing is we're negating a statement. But we're not just negating it for the contrapositive, we're also switching or flipping the order of the original statement. So the contrapositive would say, if students do not do their work, then they do not have an A. And finally, let's talk about the biconditional. The biconditional is basically just our original statement, but we add the words if and only if. So the biconditional should say, students have an A if and only if they do their work. So now we've taken this statement, students with an A do their work, and we've turned it into the conditional, the converse, the inverse, the contrapositive, and the biconditional. Now that we've done that, you guys can pause the video so that you can practice yourself doing problems number 2 and 3. Now we're going to move on to talk about the 2 types of reasoning. The main two types of reasoning are called inductive reasoning and deductive reasoning. So let's start by talking about inductive reasoning that we see on the left. Inductive reasoning just uses specific examples, patterns, or past observations to reach a conclusion. Now, this doesn't necessarily have to be true. However, inductive reasoning is kind of like what I call jumping to conclusions. That's where you take something that you've seen maybe once, twice, or 3 times, regardless of its truth, and you assume that it is a fact. Typically, any type of inductive reasoning will be in the form of a conditional statement or a biconditional statement. Now, deductive reasoning is the more proven type of reasoning. Deductive reasoning uses actual facts and statements to reach a conclusion logically. So deductive reasoning is what I would call facts and figures. Basically, if one thing is true and another thing is true, then we can assume that another thing is true. This is kind of like what we would think of as the transitive property. And the transitive property just uses deductive reasoning, again, to prove that something is true. So let's go through the following statements and let's determine if they are inductive reasoning or deductive reasoning. So let's start by reading the first statement. The first statement says, the car's battery provides power to the engine. So, if the battery is dead, the car won't start. This statement here is based on the fact that the battery provides power to the engine. What we're doing is taking a fact and reaching a conclusion logically. This statement is an example of deductive reasoning. Now let's move on to the second statement. This one says, I know Joe is a good cook because I've eaten at his house 3 times, and each time the food has been amazing. Now, none of what was said in this statement is a proven fact. However, the fact that we've eaten at his house 3 times is representative of a pattern. And the type of reasoning that uses patterns instead of facts would be inductive reasoning. Let's also read the next statement. The next statement says, the diary that is supposed to be from the 18th century might be real. It has passed a number of forensic and historical tests. Now, this also includes facts and figures. This diary is from the 18th century. That's a fact. And it has passed forensic and historical tests. So, since it's from the 18th century and it has passed forensic and historical tests, then we can logically assume through deductive reasoning that the diary might be real. Now, let's read the fourth statement. This should say, the sum of 2-digit numbers is always a 3-digit number. Now, what gives this one away is the word always. This is basically a statement that has been accepted as a fact without any real examples or facts to back it up. In fact, we could probably think in our mind of some examples as to when this isn't necessarily true. And because of it, this represents inductive reasoning. Now, you guys can pause the video if you want to practice the next 4 on your own. So now that we've talked about deductive and inductive reasoning, let's talk about another type. The third and final thing that we're going to talk about today is a counterexample. A counterexample is something that proves as an exception to the observation, and it typically is there to show that a statement is false. So think about what I just said about statement number 4. Statement number 4 says the sum of 2-digit numbers is always a 3-digit number. Now, this is only true if it can be proven every single time with no exceptions. So what we're going to do is we're going to look at the 3 statements below here, and we're going to provide a counterexample for each. We're going to find an instance where the statement that's been given is not true. So let's look at the first sentence. The first sentence says, if a food is a fruit, then it is an apple. Can you think of a fruit that is not an apple? The first fruit that comes to my mind that's a counterexample is a mango. So we can say that a mango is a fruit. This is a counterexample that proves that if a food is a fruit, then it is not just an apple. So let's try it with the second statement as well. The second statement says, all same side angles are supplementary. What we want to do is try to think of a type of same side angle that is not supplementary. Now, from my knowledge, there's only one type of same side angle that is not supplementary. Those type of angles are called corresponding angles. And our counterexample would say that corresponding angles are congruent, not supplementary. You can now pause the video to try out the third statement on your own. So now that we've talked about proofs, we've talked about different types of logical statements, we've talked about inductive, deductive reasoning, and counterexamples, you are now fully prepared for proofs and logic. Thanks for watching.